Welcome to this lesson on the fundamental principles of thermodynamics in HVAC applications. We will explore core thermodynamics concepts, including the conservation of mass and energy, the properties of substances, and the energy transformations that drive heating and cooling processes. Understanding these principles is essential for designing and optimizing efficient HVAC systems. In this lesson, we will cover the fundamental thermodynamic laws that govern HVAC systems and the properties of substances such as air and refrigerants. We will talk about conservation of mass and energy and thermodynamic properties of substances. These foundational concepts allow us to analyze HVAC operations effectively. In this lesson, we will explore the fundamental principles that govern HVAC systems behavior. You will learn how mass and energy conservation laws apply to heating, ventilation, and air conditioning processes. We will also discuss how the first law of thermodynamics helps us to evaluate energy exchanger within HVAC components, including heat transfer, work interactions, and mass flow. Understanding when an HVAC system operates under steady state or transient conditions is crucial for proper system analysis and troubleshooting. Additionally, we will introduce thermodynamic property tables, phase diagrams, and equations of state, highlighting their role in defining key parameters like pressure, temperature, enthalpy, and entropy. By the end of this lesson, you will have a strong foundational understanding of these concepts. I want you to reflect on the next. Imagine you are designing an HVAC system for a large building. What factors will you consider to ensure energy efficiency while maintaining thermal comfort? How will you balance performance and cost? Designing HVAC systems involves balancing multiple factors, including energy efficiency, cost, and occupant comfort. Engineers must consider airflow distribution, equipment efficiency, and thermodynamic principles to create a system that optimizes performance while minimizing energy waste. Conservation of mass and energy. The conservation of mass principle ensures that the total mass entering a system is equal to the mass leaving, which is critical for maintaining balanced HVAC operations. The difference between the rate of mass inflow and the rate of mass outflow is equal to the storage rate during the time in a control volume. In most HVAC systems, the flow is essentially steady, and the rate of change in mass of the control volume with respect to time is negligible. The total mass flow rate entering the control volume equals that leaving, and the mass balance equations reduced to this expression. The mass flow rate of a fluid in a duct or pipe is related to fluid density, ρ, flow area A, and mass fluid velocity V, as in this expression. The volume flow rate can be expressed as the product of flow area and velocity. The first law of thermodynamics states that energy cannot be created or destroyed, but can only change forms. In HVAC applications, this means that we must account for all energy inputs and outputs when designing heating and cooling systems. Energy may be transferred to or from the control volume by three mechanisms. Heat transfer between the control volume and its surroundings due to a temperature difference, work done or by the control volume through interactions with its surroundings, and energy carried by the flow streams entering or leaving the control volume. E is the specific energy content of the flow stream, that is the sum of the internal kinetic and potential energy. The total work of a control volume also includes the work associated with pumping fluid in and out of the control volume, the term the flow work. The flow work is combined with the internal energy as the enthalpy that we see here. The general unsteady flow and steady state energy balance relation for a control volume expressed in terms of the various components is here. In most HVAC applications, there are enable changes in kinetic and potential energy of the control volume. The flow is steady and the system is at a steady state, allowing the energy balance to be expressed as this pressure here. This transforms to zero. By applying these conservation laws, we can optimize HVAC systems, energy use, reduce inefficiency, and improve indoor air climate control. Thermodynamic properties of substances. Pressure and temperature are fundamental properties that determine the state of a substance significantly significantly influence HVAC system's operation. Pressure changes affect phase transitions, determining when a refrigerant will evaporate or condense, while temperature dictates the rate of energy transfer in heating and cooling applications. Together, these properties define how substances behave under varying conditions, ensuring efficient energy use in HVAC systems. Enthalpy is another critical property, representing the total energy content of a fluid. This includes both its internal energy and the work required to move it within a system. Enthalpy values are crucial in designing refrigeration cycles, as they determine the energy transfer that occurs during phase changes, such as evaporation and condensation. Engineers use enthalpy calculations to size HVAC components effectively and ensure optimal thermal performance. Entropy, on the other hand, measures the level of disorder or energy dispersion in a system. Higher entropy means that greater energy spread, which can influence how efficiently an HVAC system operates. Entropy helps in defining performance limits, as real systems always experience losses due to irreversible processes. By understanding entropy changes, engineers can improve system design, minimizing inefficiency and enhancing overall energy performance. Phase diagrams are essential tools for visualizing how substances transition between different states. In HVAC applications, phase diagrams illustrate saturation lines, critical points, and phase change behaviors of refrigerants and other working fluids. These diagrams provide engineers with a clear representation of where a substance exists as a liquid, vapor, or a mixture of both, ensuring proper refrigerant selection and system efficiency optimization. Refrigerants play a crucial role in HVAC systems by facilitating heat exchange through phase changes. Their thermodynamical properties, such as boiling point, latent heat of vaporization, and pressure-temperature relationship, determine how effectively they can absorb and release energy. Engineers rely on pressure enthalpy (pH) and temperature entropy (TS) diagrams to analyze refrigerant cycles, ensuring that the system operates with optimal parameters to maximize efficiency and cooling capacity. Equations of states, such as the ideal gas law, provide mathematical relationships to describe the behavior of the gases in HVAC systems. While the ideal gas law applies to gases at low pressures, more complex equations like the van der Waals equation account for intermolecular forces in real fluids. Additionally, specific heat relations at constant pressures and volume help engineers determine how much energy is required to change a substance temperature, allowing for precise calculations in heating and cooling applications. For example, here we have the ideal gas law. Gases at low pressures, such as air and water vapor at atmospheric conditions, are superheated vapors. And the relation among pressure, volume, and temperature is given by the ideal gas law, where T is the absolute temperature at Kelvin. The specific constant is equal to the universal gas constant divided by the molecular weight m of the gas. To summarize this lesson, we have covered the fundamental principles of thermodynamics applied in HVAC systems. We review conservation laws, energy balance equations, and the first law of thermodynamics in steady state and transient conditions. Understanding thermodynamic properties through property tables and phase diagrams allows engineers to optimize HVAC systems performance efficiently. HVAC systems operate under fundamental conservation laws. The mass entering a system equals to the mass leaving, and energy is conserved but transferred through work and heat. The first law governs energy balance, considering internal energy, kinetic energy, potential energy, and enthalpy to analyze energy exchanges in HVAC components. Heat transfer, work interactions, and mass flow drive HVAC system functionally. Understanding how these influence heating and cooling processes allows for improved system efficiency. Most HVAC applications assume steady-state flow, simplifying energy balance calculations. Engineers use thermodynamic properties of substances and equations of state to determine key properties like enthalpy, entropy, and specific heat for refrigerants and working fluids. In the next lessons, we will delve into mechanical work and efficiency in HVAC systems, covering components such as compression, pumps, and fans. We will learn about thermodynamic limits on performance and continue discussing how to apply these principles to real-world HVAC studies. Stay tuned as we continue building our understanding of HVAC systems. Thank you for listening to this lesson.